Today we want to talk about linear functions, which is in section 12.n of your textbook. I can't remember what n is equal to at this point, but let's talk about linear functions. Remember the context that we're in. We are going from y equals f of x, a function of one variable, which is going to be represented by a one-dimensional curve in two-dimensional space, to z equals f of x, y. That is a function of two variables representing a surface in three-dimensional space. That's I'm just going to leave that in the recording, so that's fine. That's fine. You can double speed and fast forward. So we need to talk about surfaces in R3. And we're going to start by representing them as functions of two variables. Remember that way this works. It's the same thing that we did when we built a curve out of a function of one variable. For each point along the x-axis, we calculated the function and plotted that on the y-axis. And that built a curve. We're going to do the same thing for a function of two variables, only instead of an x-axis for our set of inputs, we have an xy plane for a set of inputs. Imagine it like the floor. And then for each point in that plane, we're going to plug them in that point into the function, the x and y into that function. That'll give us a z value. We're going to plot that as the height above the floor, or if it's negative, the height below the floor, or if it's equal to 0, just put a point on the floor. And that's going to produce a surface. So we're just going to take each point, we're going to raise it up to a certain height, and that's going to produce a surface. So for example, if I take the floor as my xy plane, then this ceiling is about, how high up is the ceiling? 15 feet? Standard is 8, but I think it's 8 at the back, and there's like 9, 10, 11, so maybe about 12 feet. Let's call it 12. The ceiling would represent z equals 12. At every point on the xy plane, the ceiling is at a height of 12, and so that's a surface. Now, if we soak the ceiling, all these tiles, make them all wet, and so they start to warp, then I'll start to get some curves in my surface. They're like, oh, Leach, you can't destroy the ceiling just to make a surface. I'm like, oh, come on, it will be so cool, and it'll be funny because the students have to put out buckets, and they're like, oh, no, you're going to ruin their computers, and we'll get sued, so it was a whole thing. Oh, great. That's right. You can't afford lawyers. The plan is back on. I'm just kidding. I would have ruined my stuff as well. So we could have different heights all over the place, and that will produce a different surface. Now we're going to be concerned with the same kind of things that we were when we were drawing curves. When we draw a curve, we want to make sure it's continuous, that each point is connected to the ones beforehand. If I could just borrow Newton's description. You can draw the curve without lifting your pen from the paper. If it's discontinuous, then it's drawing, we have to lift our pencil up and put it somewhere else, and then there's this big gap. So we want to deal with continuous surfaces. We also want to deal with smooth surfaces. Smooth being our casual word for differentiable. That means we could put a tangent line at every point on our surface, or at every point on our curve. And we're going to want to think about our surface doing the same thing. So no corners, no sharp points, no creases, smooth. Our job now is one of the three things that we do in calculus. We do three things in calculus. 1, we describe stuff. 2, we do derivatives. 3, we do integrals. That's all we ever get. That's all we're doing. And we're in the describe stuff phase. We've got this new category of function that we need to apply our calculus thinking to. And it is going to be surfaces or functions of two variables. Let's start with our favorites. Linear functions. So let's start first with this linear function with just two variables, with this x and y. What do we need to describe our line? We need three things. I know it's only two things. We need a point and a slope. But what is slope? Slope is two things. A rise. I'm sorry, go ahead. Rise over run, a change in y divided by change in x. Because there's only two of them, we get to summarize it with one number. We get to describe direction with one number. But we need to have a slope, which is going to be a rise over a run. Of course, for the slope, we're going to use the obvious choice of letter to represent it, M, because it appears in slope so much. And it's going to be a rise or a change in Y divided by a run or a change in X. So the slope is rise over run, change in Y divided by change in X. So in this case, we have 2 points because we're not doing tangent stuff. Our change in Y is 5 minus 1, or 4. And our run is 1 minus a negative 2, or 3. So our slope is 4/3. So now we have all the parts that we need. We've got the rise and run, which we combine into the slope. The slope is telling us a direction, and we've got 2 points to choose from to build our line. The reason that linear equations are so simple is because they only involve 2 things, kind of 3, but 2 things. 3 calculation for our calculation, but we only need 2 things. A place to start and a direction to go. That's all we get out of a line. A place to start and a direction to go. So I'm going to pick this point, negative 2, 1, and I'm going to describe what's going on in this line. I'm going to say the Y value starts off at 1 when X is negative 2. So the Y value is 1, and it's going to increase by 4 every 3 units, or increase by 4/3 every 1 unit. This is not how I would normally write X plus 2. But here's a description of what's going on a line. Y starts at 1 when X is negative 2 and increases by 4 every 3 units. A point to start and a direction to go. If we want to read our slope as one number, 4/3, we would say Y increases by 4/3 every 1 unit. But our point to start could still be Y equals 1 when X equals negative 2. Your training might be to find the y-intercept. Sometimes you don't care about the y-intercept, as I've demonstrated here. I'd have to calculate something to find the y-intercept, and I don't want to bother you. But if I wanted the y-intercept, I wouldn't be solving any equation. I would read what's going on in the function. Y is 1 when X is negative 2, and Y increases by 4/3 every 1 unit. So when X is negative 2, my Y value is 1. To get to an X value of 0, I have to increase by 2. So I just have to add 4/3 twice. So I'll just take the 1 that I started with and add 4/3 2 times. So 3/3, 8/3, 12/3. Wait, no. I can't do arithmetic. I'm standing too close to the board. 1/3, 1 plus 4/3, but 1 8/3. That's a perfectly valid fraction. It's math class. It's like the number 4012. Most people call that 52. So if you want to be basic, like all those Brittany and Justin wannabes, you can be like all 52. But if you're like all 4012. So this is the equation using the point -2, 1. I could also write this from the point 1, 5. Y starts off at 5 when x is equal to 1. So the sentence that would describe what's going on from this equation, I'd say y is 5 when x is 1. Those split up. And y increases by 4 every 3 units. That's the rise and the run. Note that when x is equal to 1, the reason it says minus in here is that when x is equal to 1, this factor becomes 0. So we start off at 5 and add 4/3 0 times. So this x minus 1 factor says how many times we've added 4/3. So that factor x minus 1 is how many times and that's the same thing over here. This x plus 2 is the number of times we have added 4/3. Any questions? Now, in this case, I just wanted an equation of a line, so I wrote point slope equations. If we want slope intercept equations, we just have to multiply this out and write it in the form y equals b plus mx. I know you were probably trained for mx plus b. That's a terrible way to write it. Y equals b plus mx. That's better. Start off with b and add m a bunch of times. It just start with the start, right? But if we multiply all this out, we have 5 plus 4/3 x minus 4/3, just use the distributive property. And then 5 minus 4/3 is 5 and -4/3. What's 5 and -4/3? So 4 and -1/3. Wait, there's another word for that. What is it? 3 2/3? Is that right? I think that's right. No one's contradicting me. So 3 2/3 plus 4/3 x. Just distributive property for the 4/3. So that's the -4/3 because I need the 5 minus 4/3. So here's our b plus mx format. Five is from this point here. Y is 5 when x is equal to y is 5 when x is equal to 1. The way we would use this description is we'd say y is 3 2/3 when x is 0. And y increases by 4/3 every 1 unit. Anybody bothered by the fact that I mixed my mixed numbers and my improper fractions? What's that? That's true, you're not grading it. I wonder if teachers should get grades from students. That's true. You can go on Rate My Professor. But Rate My Professor is kind of like Yelp. Do you realize I can go in and write my own reviews on Rate My Professor? Yeah. I've always wanted to do this, like go on Rate My Professor and write a bunch of bad reviews of myself. Be like, oh, this guy sucks. Do not take Leach's class. Source, Am Leach. Wait a second, no, source. Totally not lying, was in his class. He's terrible. I don't know why. Then what I want to do is write increasingly violent reviews. Like, well, he's just mean to his students. And then like, there's like, man, I was in class and someone asked a question that he didn't like and he beat the student with a ruler. So, and then like next one's like, oh, that's nothing. A couple of years ago, he pulled out a sword and threatened a student to stab a student. And then after I write a bunch like that, I'll go on Professor Strike Back. I don't know if that's still exists, but it's video responses to ratemyprofessor.com reviews. And I'll be like, it's like, well, that's right. If you show up in my class, you better come correct or I'm gonna knock you out. Right? And just like have like some completely unhinged response. I don't know if the site still exists. It's really funny because some of the professors like realize that it's just fun to respond to things. And some of them like really took it seriously. Dude, you can't take it seriously. Anybody watch The Simpsons? We'll get back to linear functions in a minute. This has got to sink in for a minute because I'm describing linear functions, but it's in a different way than you might have seen. It may be a while since you thought about it. Maybe you didn't describe stuff, you just mechanically y equals mx plus b your way all through algebra. I don't know if The Simpsons is still on because The Simpsons hasn't been good for a very long time, but they used to nail things 100%. Every once in a while, they would nail something, not something in the future, but some commentary encapsulated perfectly. Does anybody remember the episode where Bart nominates Mrs. Krabappel for like a teacher award, like Teacher of the Year? Anyway, one of the episodes, Bart nominates Mrs. Krabappel for Teacher of the Year. And they show the committee watching all these submissions and all these views, these videotapes of teachers. And one of the ones they choose to show is, I use humor to reach my students. And then it like cuts to someone doing a bad impression of John Wayne and the students going, ah, ha, ha, ha. And they cut back to the committee. And the committee says, Dead Poet Society ruined an entire generation of teachers. And this is 100% true. Dead Poet Society ruined an entire generation of teachers. Because people that were going to go into the teaching profession, people approximately my age, you have to be pretty old to have been watching that movie and think, I'm going to be a teacher. I was going to be a teacher anyway, but beside the point. And thought, yes, I will do that. And no one told them, no, you will not. In Dead Poet Society, that dude has writers. The students' responses were written for them. And that dude is Robin Williams. Are you Robin Williams? No. Do your students have a script that they'll be working from? No, it's not going to be that. That is not how it is. Does that make sense? You watch all these inspirational teacher movies and you think, I'm going to be that teacher. And the fact is, probably not. It doesn't work that way. You know what I mean? Anyway. So anyway, too many teachers come in with big ideas about how they're going to change the system. The system is the way it is because it can take all that hope and energy and crush it out of you if you're not prepared to deal with And when you walk in on your first day to start teaching, you are not prepared to do it. You know what I mean? Anyway, side note. Oh, actually, side note number 2. I often have to write down arithmetic. One of my favorite things that y'all are going to do as students, I don't use paper as much anymore, but like if I hand out a piece of paper and you wrote this on the side, what would you do? Because this is a calculus class. You don't have to say it out loud because I know half of you would do this. You would write this down to get to 3 2/3, and then you would erase it. Don't react. I can see into your fucking souls. He's like, oh yeah, I would totally erase that. As if, first of all, I can't tell. And as if, second of all, I'm going to judge you. It's like, oh, I see you had to write down your fractions and then you tried to cover the evidence, minus 10 points. What am I going to do? Like, judge you? No. Just write stuff down if you need to write it down. You know what I mean? It's math. If you're trying to do math without a pencil in your hand, you're not doing math. You're just pretending. All beside the point. There's another form of equation that we have, but I'm going to need the improper fraction here. So 3 times 3 is 9 and 2 is 11. So we have another form of this equation. So I'm just going to write the 3 2/3 as 11/3. I'm going to multiply by 3 to get the standard form. So I'm going to take 3y is equal to 11 plus 4x. And then I'm going to write it in standard form, minus 4x plus 3y is equal to 11. All these different forms of lines. Notice that the standard form doesn't have as much start here and go this direction. But the coefficient of x and y do indicate some stuff about direction. That -4 and the 3. They got different signs. They're both positive. So there's some stuff to work out there. There's some information about those coefficients. Also notice that in front of the x is the 4, and in front of the y is the 3. So that seems a little bit messed up. Shouldn't the x have the run and the y have the rise? This standard form seems a little bit efficient. Any questions on equations of lines? Remember your thinking. You start at one point and you go one direction. Not the band, like the direction. Start at a point and go a direction. And you go that direction for everywhere. This is why we like linear functions. They're super predictable. What happens in 1 unit? 4/3. What happens in 10 units? 40/3. What happens in 100 units? 400/3. Nice and predictable. Exponential functions is more difficult. How's everybody okay? This has got to go up a level. We've got to go into equations of functions of 2 variables. So here we have linear functions in 2 variables. Now we need linear functions in 3 variables. So as functions, they'll be functions of 2 variables. I really should standardize my language, but anyway. Let's call it linear functions in R3. A linear function in R2 describes a line. So just guess, what would a linear function in R3 describe? We take a linear function makes a line, but in R3, what's it going to make? A plane. Perfect. That's all we do is we take a point, take a point. To make a line, we just stretch it along one dimension. Make a line. Now take that line and stretch it along another dimension, and you get a plane. We keep making linear functions. So a linear function in R3 is going to describe a plane. A linear function in R3 will describe a plane. Let's look at the format that we're going to get for our linear function. I'm going to start with point slope format. I'm going to start it as write it as a function. Z is going to start off with certain value. Here's a direction. Here's a slope in the X direction. Looks like just a line at this point. Now I'm just going to have another term for the Y's. Plus n times y minus y naught. If we describe a linear function in R2, we need a point and a slope. If we describe a linear function in R3, we just need a point and two slopes. A slope in the X direction and a slope in the Y direction. M is going to be the slope in the X direction. So this M over here is the change in Z with respect to X. And this N is going to be the change in Z with respect to Y. This plane will contain the points X naught, Y naught, Z naught. Oh, I just figured out why I have space to write this at the bottom of this page. And I didn't write the table for the line in the previous example. So let's take a look at a table of values. When we make a table of values for a function of two variables, I'm going to need two dimensions for the x and the y. I'm going to need to go horizontal on x's and vertical on y's, or the other way around. But we're going to have some x values. And then I'm going to put some y values because I need to spread this out. And then in the table will be the z values at each of these points. Now I'm going to fill in some z values. That's fine. We can just have 3. So let's suppose that at 0, 0, we have the z value is 10. And then up here, we're going to have 14. I'm making a linear function. What's going to be the function at 6, 0? If I'm making a linear function. $18 and $22. Awesome. Now let's see. When x is 0 and y is 5, let's suppose that I make a 7. Do you want to go across or down first? Across? Across it is. What should be next over here? 11. How come it's going? How do we end up at 11 here? Because it goes up by 4. The z value, if this is a linear function, the rate of change of z divided by the rate of change by the change in z, excuse me, the change in z divided by the change in x should always be the same. So if z increases by 4 when x increases by 3, that always got to be true. So here z must increase by 4 because x increased by 3. Also, if this is a linear function, the change in z divided by the change in y should be constant. So here, when we go from y equals 0, z is 10, y equals 5, z is 7, we've decreased by 3. Z is decreased by 3 when y increased by 5. So here, when x is 3, y is also increased by 5, and so z has decreased by 3. So 7, 11, 15, and 19. And then what's this going to be? This last row down here going to be 4, 8. Now we have quite a bit of information. This is a linear function. So we could see that dz dx, or sorry, delta z over delta x, z is increasing by 4 whenever x increases by 3. And the change in z with respect to y, z is decreasing by 3 when x increases by when y increases by 5. Now we have all the information we need to write an equation for this function. I've got a bunch of points to choose from. I've got a slope in the x direction. I got a slope in the y direction. So z is equal to, I need to pick a point. I'm going to start at this point here. 0, 0, 10. Z is equal to 10 when x is 0, and z increases by 4/3 whenever x increases by 1, and z decreases by 3/5 whenever y increases by 1. This would be like our slope intercept format. But I could pick whatever point I want. Here's a point 6,5. I've got when x is 6, y is 5, z is 15. Z starts off at 15 and increases by 15 when x is equal to 6. And increases by 4/3 every unit. Z is 15 when y is 5. And decreases by 3/5 every unit. So this would be point slope style. We could also write this in a standard form. Multiplying to get rid of any fractions, to try to get all integers if we can, and then put everything on one side. So if I unused slope intercept, it's easiest to put into standard form. But if I multiply everything by 15, I'll have 15z is 150 plus 20x minus 9y. And then just put the x, y, and z on one side. So I could say negative 20x plus 9y minus 15z is equal to 150. And then we have standard form. This is the same standard form we would get to if we started with a point slope style, multiply by 15. In this case, we have the 15 times 15, but we'd be getting rid of the extra stuff with the 4 times, with the 20 times 6 and the 9 times 5. So that stuff was canceled out. Any questions? Yes. So we were making the table of values up, knowing that this was a linear function. So once I set this up from 10 to 14 as x increases, since the steps in x are all 3, the z went from 10 to 14. So the z increased by 4 when x increased by 3. That has to be constant from everywhere we start. Z increases by 4 whenever x increases by 3. So from 10 to 14, 14 to 18, from 18 to 22. Z increases by 4 when x is increasing, and when x increased by 3. The next part, when I put the 7 underneath the 10, that told us how things are changing in the y direction. So when we go from 10 to 7, y decreased by 3. Sorry, z decreased by 3 when y increased by 5. So going across, I see z increasing by 4 when x increases by 3. Going down, 10 minus 3 is 7, and the y increased by 5. And that had to be true all the way across. 14 minus 3 is 11, minus 3 is 8. 18 minus 3 is 15, minus 3 is 12. That's the point that I chose to start off at. So I picked this point here, 15, when x is 6 and y is 5. So 6, 5, 15. That's my x naught, y naught, and z naught. So z is 15 when x is 6 and y is 5. Notice that 6 and 5 will zero out these two terms. So it's adding 4/3 0 times and subtracting 3/5 0 times. Is everybody okay? This is just assigning math to your default thinking. Remember that your default thinking is always linear. If you're trying to buy a car and someone's like, oh, $3,000, and the other person is $2,000, what do you get when you split the difference? A number in between, 2,500, because you both think linearly. So what you want to do is if you're coming in underneath, you want to split not linearly, but exponentially. Actually, you might be quadratic. Find the geometric mean, multiply the two and take the square root of it. All right, that's going to do it for today. I will see you all on tomorrow, more linear function stuff.